deal with electric circuits, we also inevitably have to deal with a lot of resistors and cells which are connected in various permutations and combinations. Now, when that is the case, it becomes difficult to apply simple rules to arrive at the currents flowing through each part of such circuits. A lot of work on this front was done by a German engineer, Robert Gustav Kirchhoff. In the early 1800s, and he was instrumental in providing two laws that make it very easy to deduce the currents flowing through various parts of a circuit. Two of the important laws that he stated were the junction law and the loop law. So what does the junction law state? The junction law applies mainly to the currents at a junction. So what's a junction? A junction is a point where two or more wires meet up. So the junction law basically states that the total sum of currents arriving at a junction is equal to the sum of the currents leaving the junction. So if I were to take a junction and let's assume that there are 5 wires that are connected at the junction. So if currents I1, I2 and let's say I3 are moving towards the junction and currents I4 and I5 are leaving the junction, then the junction law simply states that I1 plus I2 plus I3 should be equal to I4 plus I5. While it seems logical, there is also the necessary proof for it. It being, in a stable circuit, charges never accumulate at any point. They keep flowing relentlessly and hence this should hold true. So I1 plus I2 plus I3 are the 3 currents arriving to the junction. I4 and I5 are the currents which are going away from the junction. So the sum of the currents arriving at a junction should be always equal to the sum of the currents leaving a junction. Next, the loop law. So the loop law applies to the total potential in a closed circuit. What it states is that the algebraic sum of the change in potential across a circuit through its resistors and cells is always equal to 0. So let's break it down here. So we are looking at the algebraic sum, which means for any circuit, let's say a simple circuit, let me take a simple circuit with a resistor R and a voltage V because of a cell in the circuit. This cell is inducing a current, let's say I. Now, this is a closed loop. What this law states is that the total voltage V plus, which is the algebraic sum of the potential due to the resistor R. What is the potential due to resistor R? It is I into R. I into R, I take it with a negative sign, should be equal to 0. It equates the potentials due to cells as well as the potential difference across resistances. The net sum of both these should be 0. That's why we take the algebraic sum. If you consider this for a moment, this again should be very obvious because it is this potential source which is causing this current to move, and it's the presence of this source that's creating a particular potential difference across this resistance. So whatever potential difference is created across this resistance is because of this source. So eventually this and this should cancel out each other. So that's the significance of the loop law. So in some books you also refer to junction law as Kirchhoff's current law, KCL, and loop law is sometimes also referred to as Kirchhoff's voltage law, KVL. So Kirchhoff's current law is the same as the junction law, and Kirchhoff's voltage law is the same as the loop law. Let us consider a simple example to understand these two laws better. Consider the circuit on the board. So I have a 10-volt battery connected here and 20-volt battery connected at another end of the circuit. It also has two resistors of 5 ohms and 10 ohms each connected in the fashion shown. Now if I ask you to calculate what's the current flowing through the various parts of the circuit, how would you be able to do it? So that's exactly where Kirchhoff's laws come in. So remember that this is a junction, this is also a junction. Also, you can notice that you have two loops. There is one closed loop here and there is one closed loop over here. So let's make a few assumptions before we start applying Kirchhoff's laws. So let's assume the 10-volt battery is producing a current I1. So I1 flows out of the positive terminal of the battery and re-enters the negative terminal of the battery. Similarly, let's assume that battery of 20 volts produces a current I2. It again exits out of the positive terminal and enters back at the negative terminal. So if I1 is the current flowing into the junction, let's say this junction J1 and this junction J2. Now let's apply Kirchhoff's current law or the junction law. So if I1 is the current flowing into J1 and I2 is the current flowing into J1, what do you think will be the current here? So out of the three circuit lines that are meeting at this junction, two of them are bringing in the currents. So obviously this one should be taking out the current from the junction. And what's the total current that it should be taking out? It should be equal to the sum of I1 and I2 as per the current law. So this should be equal to I1 plus I2. Now we look at junction 2. So at junction 2, what is incoming is I1 plus I2. And I1 is going out here and I2 is going out in this direction. So again, Kirchhoff's current law or the junction law holds true again, because I1 plus I2 come here I1 goes in this direction, I2 goes in that direction. So again, the junction law holds true at junction 2 as well. Now let me consider these two loops. So I assume that the clockwise direction here, I go in the clockwise direction in this particular loop. So labeling this as loop 1, I apply the voltage law or the loop law over here. So what does the loop law say? It says the algebraic sum of the change in potential across a closed loop due to the presence of cells and resistors is always 0. So that means across loop 1, when I apply the loop law, 10 volts due to the cell and this is the source of the voltage. Now there is a resistance here, that's the only resistance in this loop, and this resistance is experiencing a current of I1 plus I2, and we know the voltage across the resistor is given by the product of the current and the resistance. So what is the current here? It is I1 plus I2, and we get the voltage by multiplying it with the resistance value. Now since these two, the algebraic sum should be 0, we apply a negative sign and this should be equal to 0. That's exactly what the loop law states. So let's simplify this. I take this term that side. So what I get is I1 plus I2 equals 10 by 5, which is equal to 2. So I1 plus I2 is equal to 2. So let me call this equation 1. Having finished loop 1, we now go to loop 2. So again in loop 2, let me assume this to be my conventional direction. Applying the junction law again to loop 2, the cell gives me a potential of 20 volts and there are two resistances over here. One is the 5 ohm resistor, the other is the 10 ohm resistor. Now across the 5 ohm resistor, I have current I1 plus I2 flowing, and across the 10 ohm resistor, it's only current I2 that's flowing. So again the algebraic sum should be equal to 0, so I take minus I1 plus I2 in brackets multiplied by 5 minus 10 into I2, and this should be equal to 0. So if I simplify this, I get 20. I take the negative terms to the other side. I get 5 into I1 plus I2 plus 10 I2 equals 0. Let me mark this as equation 2. Now from equation 1 previously that we did for loop 1, we got I1 plus I2 to be equal to 2. So let me put the value of I1 plus I2 as 2 in equation 2. So instead of I1 plus I2 here, I put the value 2. So what I get is 20 equals 5 into 2 plus 10 I2. So 10 I2, I take it to my left hand side. On the other side I get 20 minus 10. So I2 on simplification reduces to 20 minus 10, 10, 10 divided by 10 is 1. So I2 is 1 ampere. So if this is the case, then putting this value I2 equals 1 ampere back in equation 1, I get I1 also to be equal to 1 ampere. So I1 is 1 ampere, I2 is 1 ampere. So there is a current of 1 ampere flowing here, 1 ampere flowing here, and a combined current of 1 plus 1, 2 amperes flowing through the 5 ohm resistor. So with this, we have solved the circuit in terms of the current flowing through various parts. Let us consider yet another example where the circuit is slightly more complicated. You can see the circuit that I have drawn on the board. It has two voltage sources, V1 and V2, and it has 5 resistors distributed across various points of the circuit. So the moment you see this, you can notice that there are several junctions. So one is junction A, there is junction B, junction C and junction D. Similarly, there are 3 loops. First loop, second loop and third loop. So the 3 loops are triangle ABC, triangle ACD and triangle BD. Maybe I call this point as E. You can call it as triangle BD. So the 3 loops are characterized by these 3 triangles. Now, just like in the previous example, we first indicate the currents. So we assume certain currents. So one uniqueness about Kirchhoff's law is that suppose I take the direction of current in this particular circuit as flowing in this direction, but eventually let's say I get a negative value for this current. It indicates that my assumption that the current is flowing in this direction is wrong, rather the current is flowing in the opposite direction. So I'll repeat it once more. If I assume initially that the current is flowing in this direction and I name this current, let's say I2, and eventually when I get the value of I2 after all the calculations, let's say I get the value of I2 to be minus 5 amperes. It doesn't mean that there's a negative current flowing there. No, it only means that the assumption I had made initially to start with, that the current is flowing in this direction, is wrong. The current's value is still 5 amperes, but since it has a negative sign, it's an indication to me that the current is actually flowing in this direction, not from A towards B as I had initially assumed, but from B towards A, which is the true direction of the current. So this too is something that you can freely assume to start with, but automatically once you do the calculations, you stand corrected. So let's make a few current assumptions to start with. So since I have the positive terminal pointing to my left for voltage source V1, I'll assume that a current I1 starts off from the cell, and at junction A, since I don't see any other currents coming in, I assume that both these wires are the wires that are taking the current away from this junction. So current in this junction is flowing in this direction, and current in this junction is in this circuit is flowing in this direction. Which means I can assume this to be, let's say, I2, and this, since incoming is I1, outgoing in this circuit, in this line is I2, this one should be whatever remains after I2 goes in this direction. So this will be I1 minus I2. Similarly, due to this cell V2, let me assume a current I3 to be generated. Now as current I3 comes towards junction B, there is one more current I2 which is coming in towards B. The two of them meet, and again due to the junction law, the current that's flowing outwards from B is I2 plus I3. They flow over here, and here there is yet another junction. So here, what is flowing in this direction? It is the same current I1. So if I1 is flowing here, what should be flowing here? Because here I3 has to be back as I3 in here, in this part between D and D. And here it is met by I1 minus I2. So here what should be flowing? If this is coming in, this going out. Here I assume that this is coming in, there's something going out here, right? So this is then whatever is coming in, I2 plus I3 minus whatever remains after I1 goes out. So this circuit, it is I2 plus I3 minus I1. To see whether you have got this right or not, you can check by applying the junction law again at point D. So here it is I1 minus I2. Here it is I2 plus I3 minus I1. And what is going out? It should be I3. So when I sum this up, I1 minus I2 plus I2. So minus I2 plus I2 cancel each other. Plus I3 minus I1. So plus I1 minus I1 cancel. What remains is only I3, which is what is going out. So which means our assumptions are right with respect to the junction law. The next stage is to apply the loop law. So let's take each loop one at a time. So let me take this as loop 1, loop 2, and this is loop 3. So across loop L1, so again I assume I go in this direction. So this is my convention. I am going around in this direction, coming back to the starting point. So I start off with the cell which is voltage V1 minus, because the rest of them are due to the resistances. Now here current is flowing in this direction, so I continue to take it as R4 into, what is the current flowing there? I1 minus I2. And here now, be careful, the current is flowing in this direction, but you are taking it in this direction. So initially I took it with minus, I take it with minus sign whenever I come across a resistance in the flow of the direction of the current. If the direction of flow of current matches my direction of going through the loop, then I take resistance in the current as negative. But if the direction of my loop is in the direction opposite to the flow of current, then I take it with a plus sign, which means R3 into what is the current here? It is I2 plus I3 minus I1. This entire thing is equal to 0. Similarly, for loop 2, so I start over here. Now let's say I go in this direction again. So V1, now current is flowing in this direction. I2 I am going in the same direction, so I take it with a negative sign. I2 into R1. Again here I am going in downward direction. My direction of going through the loop is also in the same direction. Current is also in the same direction, so I continue to take it with a negative sign. R2 into I2 plus I3. The algebraic sum of all this should be equal to 0. Across L3, So let me assume I am going in this direction. So again, V2 minus, current is flowing in this direction, I2 I am going in this direction. So eventually I have three equations and three unknowns, I1, I2 and I3. So for three equations and three unknowns, I can solve these equations to eventually arrive at the values of I1, I2 and I3.